Okay, perfect. Welcome to Cache is King. My name is Struve, and I am the lead site reliability engineer at Kenna Security. Today, I'm going to show you how you can use Ruby to kick your performance up to the next level. Now, most people, when they hear site reliability engineer, don't necessarily think of Ruby. Instead, they think of someone who's working with MySQL, Redis, AWS, Elasticsearch, Postgres, or some other third-party service to ensure that it's up and running smoothly. For the most part, this is a lot of what we do. Kenna's site reliability team is about a year old now, but when we first formed, you can bet we did exactly what you'd expect. We went and we found those long-running, horrible MySQL queries, and we optimized them by adding indexes where they were missing, using select statements to avoid N+1 queries, and by processing things in small batches to ensure we were never pulling too many records out of the database at once. We also had Elasticsearch searches that were constantly timing out, so we rewrote them to ensure that they could finish successfully. We even overhauled how our background processing framework Rescue was talking to Redis. All of these changes led to some big improvements in performance and stability. But even with all of these things cleaned up, we were still seeing high loads across all of our data stores. And that's when we realized something else was going on. Now, rather than tell you what was going on, I want to demonstrate. So for this, I need a volunteer. I promise it's super simple. Come on, someone is easily, okay, come up here. This is kind of going to work. I already know your name, but that's good. Okay, stand right there. What's your name?
Kelly.
Okay. I've got a horrible memory. Let's try this. Ooh, I think I already forgot it. What's your name?
Kelly.
Okay. No. What's your name?
Kelly.
Maybe one more time. What's your name?
Take a guess.
just
Kelly.
Work with me.
Kelly.
Keep going. Okay. Excellent. Last time. I promise. What's your name?
Kelly.
Okay. About how annoyed are you right now?
Slightly.
Just a little bit? Okay.
Slightly.
How annoyed would you be if I asked you what's your name 1,000,000 times? Yeah, exactly. He'd be out. Okay, so get back up. I actually need you up here. So you'd be really annoyed, not to mention we'd be here all night long, and everyone's going to want food and is going to get hungry a little bit. What is one easy thing that I could do so that I don't have to keep asking this person their name? And I'll give you a hint. It involves a pen and a piece of paper. Bingo. Okay, so if you could write your name down right there. Excellent. Okay, so now that I have Kelly's name written down on this piece of paper, I no longer have to keep asking Kelly every time I need it. All I have to simply do is read the piece of paper. This is exactly what it's like for your data stores. Imagine, Kelly's your data store, I'm your Ruby application. If your Ruby application has to ask your data store millions and millions of times for information, eventually it's going to get pissed off. And it's going to take your Ruby application a long time to do it. If instead your Ruby application makes use of a local cache, which is essentially what this piece of paper is doing, it can get the information it needs a whole lot faster, and it's going to save your data store a whole lot of headache. Okay, that's all I need you for. So the moment at Kenna when we realized it was the quantity of our data store hits that was wreaking havoc on our data stores, that was a big aha moment for us. And we immediately started trying to figure out how we could decrease the number of hits we were making to the data stores to help us improve our performance. Now, before I get into all the awesome ways we use Ruby to do this, I first want to tell you a little bit about Kenna so you guys have some context around the stories I'm going to share. Kenna Security helps Fortune 500 companies manage their cybersecurity risk. The average company has 60,000 assets. You can think of an asset as basically anything with an IP address. In addition, the average company has 24 million vulnerabilities. A vulnerability is basically any way you can hack an asset. Now, with all of this data, it can be extremely difficult for companies to know what they need to focus on and fix first. And that's where Kenna comes in. At Kenna, we take all of this data and we run it through our proprietary algorithms. And then those tell our clients what vulnerabilities pose the biggest risk to their infrastructure so that they know what they need to focus on and fix first. One of the first things we do when we get all this data is we put it into MySQL. MySQL is our source of truth. From there, we then index it all into Elasticsearch. Elasticsearch is what allows our clients to really slice and dice their data any way they need to. Now, in order to index assets and vulnerabilities into Elasticsearch, we have to serialize them. And that is what I want to cover in my first story, serialization. Particularly, I want to focus on the serialization of vulnerabilities because that is what we do the most of at Kenna. So when we started serializing vulnerabilities for Elasticsearch, we initially were using active model serializers to do it. Active model serializers hook right into your active record objects. So all you have to do is define the fields you want to serialize, and it takes care of the rest. It's super simple, which is why it was naturally our first choice for a solution. However, it became a less great solution when we started serializing over 200 million vulnerabilities a day. As the number of vulnerabilities we were serializing increased, the rate at which we could serialize them dropped dramatically, and our database began to max out on CPU. The caption for this screenshot in Slack was 11 hours and counting. Our database was literally on fire all of the time. Now, a lot of people will look at this graph, and their first inclination would be to say, why not just beef up your hardware? Unfortunately, at this point, we were already running on the largest RDS instance AWS had to offer. So beefing up our hardware was not an option. Now, my team and I, we looked at this graph and we thought, okay, there's got to be some long-running horrible query in there that we missed. So off we went, hunting for that elusive, horrible MySQL query, much like Liam Neeson in Taken. We were bound and determined to finding the root cause of our MySQL woes. But we never found those long-running horrible queries because they didn't exist. Instead, what we found were a lot of fast millisecond queries that were happening over again and again and again. All these queries were lightning fast, but we were making so many of them at a time that they were overwhelming our database. So we immediately started trying to figure out how can we serialize all of this data and make less database calls when we're doing it. What if, instead of making individual calls to MySQL to serialize each vulnerability, we group all the vulnerabilities together at once and we make one MySQL call to get all the information at one time? From this idea came the concept of bulk serialization. To implement this, we started with a cache class. This cache class is responsible for taking a set of vulnerabilities in the client and then running all the MySQL lookups for them at once. We then took this cache class and we passed it to our vulnerability serializer, which still held all the logic needed to serialize each individual field, except now it would talk to our cache class instead of the database. So let's look at a specific example of this. In our application, vulnerabilities have a related model called custom fields. They basically just allow us to add any special attribute we want to a vulnerability. Prior to this change, when we would serialize custom fields, we had to hit the database to do it. Now, we could simply talk to our cache class. The payoff of this change was big. For starters, the time it took to serialize vulnerabilities dropped dramatically. Here's a console shot of how long it takes to serialize 300 vulnerabilities individually. It takes us just over 6 seconds. And that's probably a pretty generous benchmark, considering it would take even longer when the database was under load. If instead we serialize those exact same 300 vulnerabilities in bulk, boom, less than a second to do it. These speedups are a direct result of the decrease in number of database hits that we have to make to serialize these vulnerabilities. To serialize those 300 vulnerabilities individually means we have to make 2,100 calls to the database. 2,100. To serialize those 300 vulnerabilities in bulk means we only have to make 7. Boom, again. As you can probably glean from the math here, it's 7 calls per individual vulnerability, or 7 calls for however many vulnerabilities you can group together at once. In our case, we are usually grouping these vulnerabilities in batches of 1,000. So we roughly decreased the number of hits we were making to MySQL from 7,000 down to 7. This drop in database requests is plainly apparent to see in this MySQL queries graph, which shows the number of requests we were making before and then after we deployed the bulk serialization change. With this large drop in requests also came a significant drop in database load, which you can see on this RDS CPU utilization graph. Prior to the change, we were maxing out our database at 100%. After, we're sitting pretty chilly around 25%. And it's been like this ever since. The moral of the story here is, when you're processing large amounts of data, try to find ways that you can use Ruby to process that data in bulk. We did this for serialization, but it can be applied anytime you find yourself processing data in a one-by-one manner. Take a step back and ask yourself, is there a way I could process this data together in bulk? Because one database call for 1,000 IDs is always going to be faster than 1,000 individual database calls. Now, unfortunately, the serialization saga doesn't end here. Once we got MySQL all happy and sorted out, then suddenly Redis became sad. And this, folks, is the life of a site reliability engineer. A lot of days, we feel like this. You put one fire out, you start one somewhere else. You speed one thing up, and the load transfers to another. In this case, we had transferred the load from MySQL to Redis, and here's why. When we index vulnerabilities into Elasticsearch, we not only have to make calls to MySQL in order to get the data to serialize them, we also have to make calls to Redis to know where to put them. In Elasticsearch, vulnerabilities are organized by client. So whatever client a vulnerability belongs to determines where the vulnerability is going to get put in Elasticsearch. To figure that out, we store that information in Redis. So we make a GET request to Redis to figure out where it needs to go. When preparing vulnerabilities for indexing, we gather all the serialized vulnerability hashes, and one of the last things we do before sending them to Elasticsearch is we make that Redis GET request for each vulnerability based on its client. Now, these vulnerability hashes are often grouped by client. So this Redis GET request is often returning the same information over and over again. Now keep in mind, all these Redis GET requests are super simple and very fast. As you can see, they take a millisecond to execute. But as I stated before, it doesn't matter how fast your requests are. If you're making a ton of them, it's gonna take you a long time. We were making so many of these simple GET requests that they were accounting for roughly 65% of our job runtime, which you can see in the table and is represented by the brown in that graph. The solution to eliminate a lot of these requests was Ruby. In this case, we used a RubyHACK to cache the Elasticsearch index name for each client. Then, when looping through those serialized vulnerability hashes, instead of hitting Redis for every single one, we would simply reference our client indexes hash, which meant we only had to hit Redis once per client instead of once per vulnerability. So let's look at how this paid off. Given these 3 example batches, no matter how many vulnerabilities are in each batch, we're only ever going to have to hit Redis 3 times to get all the information we need to know where to put these vulnerabilities in Elasticsearch. As I mentioned earlier, these batches usually contain 1,000 vulnerabilities apiece. So we roughly decreased the number of hits we were making to Redis 1,000 times, which in turn led to a 65% increase in job speed. Even though Redis is fast, using a local cache is faster. To put it into perspective for you, to get a piece of information from a local cache is like driving from downtown Salt Lake City to the airport to get it. It's about a 15-20 minute drive, pretty easy. To get that same piece of information from Redis is like driving from downtown to the airport, then flying to San Francisco to get it. Redis is so fast that it's easy to forget that you're actually making an external request when you're talking to it. And those requests can add up and have an impact on the performance of your application. So with these maps in mind, remember, Redis is fast, but a local Ruby cache, such as a hash cache, is always going to be faster. Now, these are 2 great ways that we can use simple, plain old Ruby to replace data store hits. Next, I want to talk about how you can make use of whatever framework you're using to replace your data store hits. So this past year at Kenna, we sharded our main MySQL database. And when we did, we chose to do it by client. So every client has its own database where all of its own information lives. This means when we're looking up data, say we're looking up a client or an asset for a client, we have to know what shard database to look at in order to get that information. This means our sharding configuration, which tells us exactly what client belongs on what sharded database, needs to be easily accessible because we have to access this information every single time we make a MySQL request. Given those requirements, we first turn to Redis to do this because Redis is fast and the configuration hash we were storing was not very large at first. Eventually, that configuration hash grew and grew as we added more and more clients. Now, 13 kilobytes might not seem like a lot of data, but if you're asking for 13 kilobytes of data millions of times, it can add up. In addition to our growing configuration hash, we were also continually adding workers on the back end to help us process more and more data, until eventually we had 285 workers chugging along at once. Now remember, every single time one of these workers makes a MySQL request, it first has to go to Redis to get that 13 kilobyte configuration hash. All of this quickly added up, and soon we were reading 7.8 megabytes per second from Redis, which we knew was not going to be sustainable as we continued to grow and add clients. When we started trying to figure out how we would solve this problem, one of the first things we decided to do was take a look at Active Records Connection Object. Active Records Connection Object is where Active Records stores all the information it needs to know how to talk to your database. So naturally, we thought it might be a good place to find somewhere we might be able to store this configuration hash. So we jumped into a console to check it out. And what we found was not an Active Record Connection Object at all. Instead, it was this Octopus proxy object that our Octopus sharding gem had created. This was a complete surprise to us. So we immediately started digging into the gem source code, trying to figure out where the heck this Octopus proxy object came from. And when we found that Octopus proxy object, much to our delightful surprise, it already had all of these great helper methods that we could use to access our sharding configuration. Boom, problem solved. Rather than having to hit Redis every time we made a MySQL request, all we simply had to do was reference our local Active Record Connection Object. One of the biggest things we learned from this whole experience was how important it is to know your gems. It is crazy easy these days to include a gem in a gem file, but when you do, make sure you have a general understanding of how it works and how it's configured. I'm not saying you guys need to go and read the source code for every single one of your gems, because that would take forever. But consider this. The next time you set up a gem, consider setting it up manually in a console with logging turned on so that you can see what it's doing and how it's being configured. If we had had a better understanding of how our Octopus sharding gem was configured, we could have avoided this entire Redis headache. However, regardless of where the solution came from, once again, caching locally, in this case using our framework as a cache, is always going to be faster and easier than making an external request. These are 3 great ways that you can use Ruby to replace your data store hits. Next, I want to shift gears and talk about how you can use Ruby to avoid making data store hits you don't need. Now, I'm sure some of you guys are looking at this thinking, I already know how to do this, right? But let's hold up a minute, because this might not be as obvious as you think. For example, how many of you have written code like this? Come on. I know I have. Yeah, that's okay. There you go. This code looks pretty good, right? If there's no user IDs, we're going to skip all of this user processing. So it's fine, right? Fortunately, that assumption is false. It's not fine. Let me explain why. Turns out, when you execute this where clause with an empty array, you're actually going to be hitting the database when you do. Notice, this where 1 equals 0 statement This is what active record uses to ensure no records are returned. Sure, it's a fast 1 millisecond query, but if you're executing this query millions of times, it can easily overwhelm your database and slow you down. So how do we update this chunk of code to make our site reliability engineers love us? You have two options. The first is by not hitting the database unless you absolutely have to. And you can do that by adding an easy peasy array check. By doing this, you can avoid making that useless database request and ensure that your database is not going to be overwhelmed by useless calls. In addition to not overwhelming your database, this is also going to help speed up your code. Say you're running this block of code 10,000 times. It's going to take you over half a second to run that useless MySQL lookup 10,000 times. If instead you add that simple line of Ruby to prevent that MySQL lookup and you run a similar block of code 10,000 times, less than 1/100th of a second to do it. As you can see, there's a significant difference between hitting MySQL unnecessarily 10,000 times and running a plain old line of Ruby 10,000 times. And that difference can add up and have an impact on the performance of your application. A lot of people will look at that top chunk of code, and the first thing they'll say is, what are you going to do? Ruby's slow. But that couldn't be further from the truth, because as we just saw, the simple line of Ruby was hundreds of times faster. In this case, Ruby is not slow. Hitting the database is what's slow. Keep an eye out for situations like these in your code where it might be making database requests you don't expect. Now, some of you Rails folks might be looking at this thinking, I'm not exactly writing code like that. Actually, I chained a bunch of scopes to my where clause, so I have to pass that empty array, otherwise my scope chain breaks. Thankfully, even though Active Record doesn't handle empty arrays well, it does give you an option for handling empty scopes, and that is the none scope. None is an active record query method that allows you to return a chainable relation with 0 records, but more importantly, to do it without querying the database. So let's see this in action. We know from before, if we run that where clause with our empty array, we're going to hit the database when we do. And we're going to do it with all those scopes attached. If instead we replace that where clause with the none scope, we're no longer hitting the database, and all of our scopes still chain together successfully. Be on the lookout for tools like these in your frameworks that will allow you to work smarter with empty data sets. And more importantly, never, ever assume your framework or gem is not making a database request when asked to process an empty data set. Because you know what they say about assuming. Ruby has so many easily accessible libraries and gems, but their ease of use can lull you into a sense of complacency. Once again, make sure when you're using a library, a gem, or a framework that you have a general understanding of how it works under the hood. One of the easiest ways to gain a better understanding is by logging. Set your logging to debug for your framework, your gems, and every one of your related services. When you're done, start loading web pages, start running workers, even jump into a console and start running some commands. When you're done, take a look at the logs that are produced. Those logs are going to tell you a lot about how your code is interacting with your data stores. And some of it might not be interacting how you would think. I cannot stress enough how valuable something as simple as reading logs can be when it comes to making optimizations in an application, and when it comes to finding these useless database hits. Now, this concept of using Ruby to prevent useless data store hits doesn't just apply to MySQL. It can apply to any data store you're using. At Kenna, we used Ruby to prevent data store hits to Redis, MySQL, and Elasticsearch all at once. And here's how we did that. Every night at Kenna, we build these beautiful intricate reports for our clients using their asset and vulnerability data. These reports start with a reporting object, which holds all the logic needed to know exactly what assets and vulnerabilities belong to the report and how we're going to build it. Then, every single night, to build that beautiful page you just saw, we have to make over 20 calls to Elasticsearch and multiple calls to Redis and MySQL. Now, our team did a lot of work to make sure all these calls were extremely fast. But even so, it was still taking us hours at night to build all these reports. And soon, the number of reports in our system grew so much that we couldn't finish them all overnight. Clients were literally waking up in the morning and their data was not ready for them, which was a big problem. When my team and I started trying to figure out how we would solve this problem, the first thing we did is we decided to look at our existing reports in our system. So the first thing we looked at was, okay, how many reports do we have? Just over 25,000. That was a pretty healthy number for us, considering only a few months earlier, we had only had a couple thousand. The next thing we decided to look at was, okay, how big are these reports? The bigger the report, the longer it's going to take to build. The smaller, the quicker it's going to take to build. We thought maybe there might be some way we could split them up. So we took a look at the average asset count for each report. Just over 1,600. Now, if you remember back to the beginning of the presentation, I mentioned that our average client has 60,000 assets. So when we saw that the average report only contained 1,600, that seemed pretty low to us. So the next thing we thought was, okay, how many of these reports have 0 assets or are blank? Woo! Over 10,000. Over a third of our reports are blank, which means they contain no assets and no data. And if they contain no data, what is the point of making all these Elasticsearch, Redis, and MySQL calls when we know they're going to return nothing? Light bulb, don't hit the data stores if the report is empty. By adding a simple line of Ruby like this to skip the reports that had no data or were blank, we took our processing time from over 10 hours down to 3. By adding that simple line of Ruby, we were able to prevent a bunch of worthless data store hits, which in turn sped up our processing speed tremendously. This strategy of using Ruby to prevent useless data store hits, I like to refer to it as using database guards. In practice, it's super simple, but I think it's one of the easiest things to overlook when you're writing code. Okay, we're almost there, guys. This last optimization story I have for you actually happened pretty recently. So if you remember those rescue workers I talked about at the beginning of the presentation, as I mentioned, they run with the help of Redis. One of the main things we use Redis for is to throttle these rescue workers. So given our sharded database setup, we only ever want a set number of workers to work on a database at any given time. The reason being is in the past, we found too many workers working on a database would overwhelm it. So to start, we pointed 45 workers at each database. Now, after making all of these improvements I just mentioned, we figured, okay, it's probably time to bump up the number of workers we're running so that we can increase our data throughput. So we bumped the number up to 70. And after we did this, we kept a very close eye on MySQL, because that was our main concern. But it was still happy as a clam. So my team and I, we were pretty proud of ourselves at this point, and we kind of celebrated the rest of the day. But the celebration didn't last for long, because as we learned earlier, often when you speed one thing up, the load transfers to another. In this case, MySQL was happy, but then overnight, womp womp. We got a Redis high traffic alert. And when we looked at our Redis traffic graphs, we saw at times we were reading over 50 megabytes per second from Redis. So that 7.8 from earlier, that's not looking so bad now. All of this traffic was being caused by the hundreds of thousands of requests we were making trying to throttle these workers, which you can see on this Redis request graph. Basically, before any single worker can pick up a job, it first has to go to Redis and figure out how many workers are already working on that database. If 70 are already working on the database, the worker won't pick up the job. If it's less than 70, then the worker knows it can pick up the job. All of those requests were overwhelming Redis and eventually ended up causing a lot of errors in our application, like this Redis connection error. Our application literally started dropping important Redis requests because it was so overloaded by all of the throttling requests coming from our workers. Now you can bet, given what we had learned from all of our previous experiences, our first thought was, how do we use Ruby to solve this? Could we cache the worker state in rescue somehow? Could we maybe cache it in active record? Unfortunately, after pondering this problem for a few days, no one on the team came up with any good ideas. So we decided to do the easiest thing we could think of. We removed the throttling completely. And when we did, the result was dramatic. There was an immediate drop in requests being made to Redis, which was a huge win. But more importantly, those Redis network traffic spikes that we had been seeing overnight were now completely gone. As soon as the load on Redis decreased, all those application errors we had been seeing resolved themselves. Following the throttling removal, we of course kept a close eye on MySQL because once again, that was our main concern. But it was still happy as could be. So the moral of the story is sometimes you need to use Ruby to replace your data store hits. Sometimes you want to use Ruby to prevent your data store hits. And other times, you might need to just straight up remove the data store hits you no longer need. This is especially important for those of you who have fast-growing and evolving applications. Make sure you're periodically taking inventory of all the tools you're using. And if you're not using something, get rid of it, because it might save your data store a whole lot of headache. As you all are building and scaling your applications, remember these 5 tips. And more importantly, that every data store hit counts. It doesn't matter how fast it is. If you multiply it by 1,000,000, it's gonna suck for your data store. You wouldn't just throw dollar bills in the air, would you? Because a single dollar bill is cheap. Don't throw your data store hits around, no matter how fast they are. Make sure every external request your application is making is absolutely necessary, and I guarantee your site reliability engineers will love you. And with that, my work here is done. Thank you all so much for your time and attention. Does anyone have any questions? Yeah, excellent. So the question was, what metrics do we look for to indicate that there's going to be a problem with the data store? One of them is literally just the number of requests. We're looking at that, and then the CPU, the load that the database is coming under. And eventually, if it gets so bad, you end up actually seeing those errors. So one of the nice things in Datadog is you can look at all the requests you're making, you can look at the percentage of errors that are being created, and if that error percentage starts to creep up or go over a certain amount, that usually indicates that there's a problem. Yeah, so the question was what tool and how do we find those hot points for queries that we can actually optimize and combine? Honestly, a lot of them were found through logging. We would use Datadog to find hot spots, and usually, because of the way Datadog's set up, is you can find the hot spots and where they are in your application. So, okay, this worker, this looks like a hot spot. When it runs, it's making a ton of requests. So then what we'd do is we'd literally go into a console, we'd run that worker in line, and we'd look at the database calls that it was making. Yeah, with our eyes. Also, the other thing that Datadog gives you is Datadog logs a bunch of the requests. So we can go into Datadog, and it'll say, when this worker ran, you made 100 calls to get the client ID, or to get this client from the database. So that's one of the easy ways that we can do it without actually explicitly having to read all the logs. But honestly, a lot of the times, we'll just throw it in a console, and it's pretty apparent when you've got a request over and over again. You're going to know pretty quickly, what's wrong. Yeah, so we had one query that we were not able to bulk. But thankfully, that query actually doesn't apply every time we run a serialization for a vulnerability. So it was kind of, as luck would have it, it didn't affect the outcome so much. But the majority of them, we bulked together. And as you could see from the graphs, it was a huge improvement for us. Great. So the question was, how do you handle cache busting? So as you can see, a lot of the caches that we're dealing with are just local caches. So they're only surviving for the lifetime of the worker or the thread that they're actually running in. In terms of caching other things in our application, like things in Redis, when we started, we had no default expiration. That is a horrible idea. Anytime you guys use Redis, set a default expiration. We had keys in Redis that were like 5 years old. It was bad. So one of the best ways is set a default expiration. Pick something like 1-2 days, depending on your data. And then honestly, you gotta set the cache expirations, and you kind of gotta fiddle with it a little bit. So, depending on your user scenario, maybe you set it to an hour and you think, okay, no one really noticed. Let's try 3 hours. Oh, shoot, someone noticed their data was stale. Okay, let's maybe bring it back down to 2. So it's definitely something you got to kind of go through a couple of iterations to get. No, we did not. So the question was, when we were using that hash cache to hold all of the index names, did we run into any memory issues? We did not, because the index names were literally, they were short little, 50-character string. And like I said, we were usually holding, like a handful of them in memory at once. So, yeah. So the question is, did we find, what Redis tools did we use for monitoring to find some of these issues that came up? And honestly, a lot of times we just used Redis Monitor. So when the issues started happening, we would turn on the monitoring and log for, a few minutes, all the hits being made, and then we would go through and we'd look at those requests being made and try to figure out which ones were, we were making in exorbitant quantities or which ones were slow. One of the nice things about Datadog is it'll record, what your slowest requests are, and so that's definitely very helpful. But yeah, it's definitely an art form. You kind of gotta play with it. Anyone else? All right, I'm happy to talk to anyone about this at the meet and greet later. So thank you guys.